It's wonderful to contemplate the incredible diversity of frequencies of light circulating in our environment on a spring day. Now, as to how we interpret that as color and brightness and sound and pitch and tone, we'll talk about that a little later. What we want to do today is we want to verify, we're going to look at two things, traveling waves and standing waves. And with traveling waves, we're going to verify the periodic nature of wave motion and how it obeys all the sorts of relations we studied before. With standing waves, we're going to get a hint at how precisely mathematical the relations of waves are. So let's get started. Now, our basic wave shape, ideally, right, if this is amplitude A, this is equilibrium, and this is negative A, and this is time, our wave shape at any given point is going to oscillate. It's going to diverge from equilibrium in the positive direction, and a restoring force is going to pull it back to equilibrium, and it's going to overshoot, right? Everything that we remember. And so when we think about waves, physical waves in the environment, we want to always be keeping in mind the elements of periodic motion. Disturbance, equilibrium, period and frequency, and amplitude. And when we look at a graph like this, if we want to identify a cycle, we take a point on the graph, for example, here at equilibrium. We follow the motion, right? It's back at this position here, but it's going in the other direction, so we keep going. We find that that's one cycle. Now, it's also easy to identify cycles by going crest to crest, or trough. We don't have enough to trough to trough. So if we start our cycle here at the crest, right, and we wanted to annotate this graph, we would say that's one wavelength, right, or the distance for one cycle. And we would find that this is our amplitude. And we would, looking at time, we would see how long it took to go from here to here, and we would find that that's our period. And from that, we could calculate frequency. Now, I want to consider three types of wave that we got in our examples yesterday, and we want to verify that they're operating according to these periodic principles. So let's take first a water wave. Okay, undisturbed water is going to develop a surface, right? A certain depth, and here's the water down here, and up here is air. Right, this is our equilibrium. The surface of the undisturbed surface of the water is equilibrium. Now, if we took a stone, right, like that, we dropped it in, right, it would hit the surface here, and it would push down under, right, it would push through, and then it would sink to the bottom, right? So the stone would end up there. Now, when it's pushing through, though, what it's going to do is it's going to push the water molecules down below the equilibrium point. And then what's the restoring force going to be? Well, have you ever pushed a beach ball or a ball of some sort down into the water? It pushes back up, right? So that restoring force is buoyancy. So when down here, a buoyant force is going to attempt to return these water molecules back to equilibrium. Once they get here, though, and this came out really nicely in those slow motion videos, the water is going to overshoot, right? And as soon as that water overshoots equilibrium, comes up here, suddenly there's going to be a gravitational force pulling down. So when the water molecules are pushed below, you get the buoyant force put as restoring force, and when they're above, it's the gravitational force. And by the influence of each water molecule and the water molecules next to it, that oscillation will then travel across the surface. Now, let's take a look at, so we have our disturbance. Now, let's think about a sound wave. This is harder because it's not visible to us, right? But say we have a bell clap, a bell, you know, this is the side of a bell here, right? And we whack it right here with a hammer or a clapper of some sort. This is our equilibrium right here, the natural shape of the bell. When we whack it with something, we're going to deform it even slightly to here. And once it's been deformed from its equilibrium position, its own elasticity will push the bell that way. And when it hits equilibrium, it will overshoot over to here. And then the elasticity will pull it back. What happens there, you know, a bell is highly, has a very high K value, so its elasticity is really strong and stiff. That's going to vibrate really quickly. And when it's pulled back like this, by the initial hit, the air molecules around it are going to be expanded and they're going to go to a lower pressure. Then when the bell moves to here, it's going to compact the air molecules in front of it. So they're at a higher pressure. That means the equilibrium is the ambient air pressure, and the initial strike lowers it below the ambient air pressure, and then by the tendency of fluids to seek an equal pressure, it will go back to equilibrium. And what you get then are alternating regions of compression and less dense, then compression and less dense in that manner. So that this would be a crest, a peak. And this would be another peak. This would be our wavelength. We know the wave speed is determined by the material. Let me give you a close-up of that. And that wave would then propagate off exactly at the frequency that the bell is vibrating. Now, last example we'll look at is a string on, say, a guitar or a violin or something like that. Now, this string has a certain tension, right? And that's adjusted at the top, at the neck. And its equilibrium position is the natural position between the 2 points where it's tied down. When a person either draws the bow across the string or pulls at it with the pick, the string is pulled away from equilibrium like that. Then, by its elasticity, the tension in it, it's going to be driven back. That's the restoring force. When it hits equilibrium, it will overshoot. And then it will be driven back that way again. And so by that restoring force, it's going to start vibrating at a certain frequency, its natural frequency. If we tighten it, increase the tension, that's higher restoring force, it'll vibrate at a higher frequency. Now, that's our basic verification. That's what that waves operate according to the exact principles that we saw in periodic motion. Now, once that happens, once that disturbance occurs and the wave gets started, in principle, it will go off to infinity. It will just travel off to infinity. Now, in real life, there's going to be damping forces like friction and things that will gradually take the energy away from it. In principle, though, it goes off forever. So say we have the sun right here, right? Right, and in the sun there is a disturbance, say nuclear fusion reactions, and these cause electromagnetic waves to go off in all directions. not just a circle, right, a sphere. So whatever the initial energy of that was, these electromagnetic waves transmit that energy. The larger the sphere, the further away you get, the less energy you have per unit surface area. Now the Earth is way out here, right, 93 million miles away. But these expanding waves are going to travel. They're going to go on, in principle, forever. At a certain point, though, some of them are going to hit the Earth right here. You know, it's 93 million miles away. It's a very small amount. But that's what we get when we see the sun. When you see something in the environment, what's happening is that tiny, minuscule amount of the sun's light is going to hit that object. Say it's a leaf. Most of it will be absorbed. The green light is reflected off, and it enters our eye. Our eye then interprets that as color and brightness. And that's the basics of sight. So that's the tendency of a wave to propagate or travel, right, perpendicular to the wave front forever, in principle. Now, we have found, however, that if we confine a wave in some way, if we block it in some way, an interesting thing happens. And you can think about a swimming pool. Say you're in a swimming pool, right? If that swimming pool is infinitely in surface area and you jumped off the high dive, the disturbance you make would then propagate off as a wave forever. However, we know that there are walls at the end of the pool. And what happens when the wave hits the wall? It reflects, right? And here's the thing. That reflected wave is then going to interact with any more incoming waves. And we know by superposition that when the two waves, the reflected wave off the boundary and the originated wave, hit each other, they're going to add up. And so if you have crest to crest, you're going to get a higher wave. If the trough of the originating wave hits the crest of the reflected wave, it'll cancel. Now, the thing is, if we set things up just right, there's a natural frequency to that reflection and that interaction, and we can get what's called a standing wave. So, in a string in elasticity, right, all musical instruments with strings, right, they tie the string down at one end, and then they tie the string down at the other end. And you can change that with frets, etc. And so here is our equilibrium position of the string. And this has a certain length, L. Now, if we disturb this string, pull it this way, we'll create a wave, right? And that wave will go towards the end here, and then it will reflect off, and it will reflect off here, and that reflection will occur internal to the string. And those reflected waves will start to interact with each other. If you can hit the natural frequency, they'll start to resonate. And at that point, you'll get a standing wave like this. We call that the fundamental. It's the lowest frequency at which the string will resonate. And we also know that one wavelength of a wave is not this, right? It's that. So what we have here at the fundamental is 1/2 of the wavelength. And there's going to be a certain speed here so we can determine frequency. So everything then works out. The velocity of the wave, of the medium, is going to equal the frequency times the wavelength. Now, same string, right? That's going to have a second frequency where you get the whole wavelength on there. And we call this the second harmonic. And the second harmonic frequency is an integer multiple, or 2 times the fundamental frequency. And we can see here that we now have one whole wavelength at this frequency. And there will be a third harmonic. Oops. In which this is now lambda. That's the third harmonic. and frequency 3 is going to equal 3 times the fundamental frequency. So in principle, this string can support an infinite number of harmonics, starting with the fundamental, and each of these frequencies is going to have a smaller wavelength because it's a higher frequency, right? This is 3 times that. Now, when we hit the 4th harmonic, it'll go like this. And we see that the wavelength is going to equal half of the string length. And that's your basics. You'll have to study that a bit in the book in order to handle the problems. But it's perfectly mathematical and perfectly proportional. And that's why the Greeks understood that the length of instruments, both stringed and wind instruments, was a key to the idea of harmonics. And for Pythagoras, that was the basis of the world. So that's your basic introduction to a standing wave. Now, I'll just add parenthetically, we won't go through it now, but wind instruments also provide a boundary to confine a wave, a sound wave in air. Right? And you can verify this by getting a soda bottle or something like half full and blowing over the top of it. At a certain point, you'll start to hear it resonate, right? You hear the sound rise, and at that point, you've hit one of the frequencies. All right, so that's your basic introduction. Now, you're going to have to do a little bit of studying to get the math down, study the diagrams in the book, and today you'll be doing a quick computer simulation with standing waves and then the lesson checks, and I will see you in discussion.